All right, everybody, clearly we're still missing some folks here, but we'll go ahead and get started. So if you want to, we're gonna start with a review problem, talking about those heating curves. So just a reminder, heating curve is when you've got temperature on the y-axis in Celsius usually, but it can be whatever temperature units you want. And then energy in along the x-axis. So we're dumping energy into a system and we're looking what happens to the temperature as we add energy. So for this, we're talking about a piece of ice that starts at minus 23 Celsius. It is going to end up at steam at 125 Celsius. So try and draw the steps there. See what you can do. I'll give you a few minutes.
Oh, look at this. See anything? What was your percent or?
Okay, so what is yo mismo, this is muy smart cuando vi que memory, cuando the thought is pero 90%.
That's very.
Bitch, but every 2 minutes.
Pero sick days, so entonces, que no sería.
Yo no más I just put it.
I can. But you should have seen me when I entered flow state in this.
Yo want him to be my
And I entered flow state.
No, yo no tenía
Y los jueves como antes de las 3 de la noche. Entonces,
So just start with where we start. Starting minus 23 Celsius. If we start with ice at minus 23 Celsius, if we add energy into it, what happens?
Rises in temperature.
Temperature is going to go up until what? Until we get to the melting point. Which for water we know is at 0 Celsius. If we're doing this for something that's not water, and you don't have the phase change temperatures memorized, then I'll give you the phase change temperatures. For water, I kind of expect you to know that it melts at 0 Celsius and boils at 100 Celsius. But for anything else, if we were doing this for ethanol, if we were doing this for iron, if we were doing this for literally any other substance, I would have to give you those melting points and freezing and vaporization points. Right, so don't worry if you don't have everything memorized. But this is one of the reasons why we use water as the most common example. It's one, we have the most everyday experience with it going through those changes. And two, those people have those numbers memorized, or at least pretty quickly into this class. So what happens when it gets to 0 Celsius? It flatlines, because what's happening?
All the energy is continuing to go into the transformation.
All the new energy we're adding is going to go into melting the ice. And I kind of drew this, and then I didn't leave adequate space to draw all 5 steps here, so I'm gonna draw over the writing here for this next part. So once all the ice is melted. Now we have a bunch of liquid water at 0 Celsius. If we keep dumping energy in. Temperature goes up again, right? Until what?
Flatlines again.
Yeah, at 100 Celsius, once we get to boiling point. So this is obviously not to scale. Really doesn't like me drawing close to the edges. So once we get to 100 Celsius. We have another phase change. Phase changes are always gonna be flat on these heating curves because all that extra energy is going into the phase change. Not into temperature change. Alright, and then it stops eventually. When all of the liquid water is boiled off. This is where our everyday experience kind of is a little bit lacking in some respects, right? Because we never boil a pot until all the water is gone, right? We pretty frequently see ice melt until it's entirely becomes liquid. Very rarely do we actually boil water until it's all gone. And then even if we did, we don't really have a way to do this next step, which is if you keep that steam contained and you continue heating it, it'll start increasing in temperature again. Right, so because usually we just have an open system when the water boils off as steam, the steam's just gone and as humidity into the surroundings. But this is pretending we have a way to continue heating that sample of gas. And it just does the same thing. Once again, it's going to continue increasing in temperature until we get to our final temperature here. And so we don't have to start at minus 23 Celsius. We could start as low as we wanted. What's the absolute lowest temperature we could start with the ice? What is 0 Kelvin in Celsius? 0 Kelvin's absolute zero, right? So you can't get any colder than absolute zero. Who remembers the conversion for Kelvin to Celsius? Temperature in Kelvin is temperature in Celsius plus 273.15. So if you plug in 0 Kelvin and solve for temperature of in Celsius, it's minus 273. So you can't get any colder than negative 273.15 Celsius, which corresponds to about negative 400 something Fahrenheit. But we never really do anything with Fahrenheit. Unless it's just in everyday life, so don't worry about that. So we could start this as low as negative 273 Celsius. I like to pick numbers that are a little bit more reasonable, so unless I was going to like an astronomy application, we're not really gonna see anything dramatically colder than minus 23 Celsius, because that's what a residential freezer will get about to minus 23 Celsius. Which if we put that in Fahrenheit winds up being, I wanna say just below, I think between 0 Fahrenheit and minus 10 Fahrenheit, if I'm remembering properly. Is there a theoretical maximum? If we kept warming up this steam, could we go indefinitely? More or less. There's probably an absolute maximum temperature that you could have. But that's for the theoretical physicists to debate.
Yes, so heat is kinetic energy, is that right?
Correct.
So would there be a temperature that equates to the speed of light?
That's exactly what the theoretical maximum is. So if you remember that kinetic energy is 1/2 mass times velocity squared. We do actually have an absolute maximum speed limit for the speed of anything in our universe is the speed of light. Nothing moves faster than the speed of light. So the maximum speed that anything could go would be speed of light here. Turns out that when you start getting close to the speed of light though, we start getting relativity involved. And it's not as easy as just keep dumping energy in at some point, because when you start getting close to the speed of light, if you double the amount of energy that you put in, you only get halfway to the speed of light, and then you get double the amount of energy again, and you get halfway again. So you asymptotically approach the speed of light. You can never actually reach the speed of light, even if you put a near infinite amount of energy in. So basically, we're gonna ignore that because this isn't a physics class. But there is a hard limit to how high the temperature can go, but we're never gonna get there. So we don't need to worry about it too much. And we're talking well past the temperature of a star. Alright, but these middle pieces though, these phase changes really aren't gonna change very much. Where we start and where we end can change a little bit, but for water, it's always gonna have a plateau at 0 and it's always gonna have a plateau at 100. So drawing these heating curves should feel like, for the most part, it's the same thing every time. It's just where are you starting and where are you ending? Are we ending here before we even get to boiling? Or are we going up to boiling and stopping? Or are we going all the way through boiling and continuing on? But all of that's just going to be in the problem. You just have to look at what steps the problem is describing and kind of decide on this graph, where are you starting and where are you ending? But the shape of it's always the same. Questions on heating curves? Not yet. Why is this useful? Because this is going to organize our thoughts for the next question, which is, if you have a mass for the ice, how much energy is it going to take for that entire process? So starting at minus 23 Celsius is ice, going to 0 Celsius, melting the ice, bringing water at 0 Celsius up to 100 Celsius, and then boiling the water, and then continuing to heat it. So we have 5 steps here. Right, I'm going to draw a very small version just so we can organize our thoughts. Temperature goes up, phase change. Temperature goes up, phase change. Temperature goes up. So this is where we ended last week. If you have a heating curve or a cooling curve, this is a really convenient way to plot out our steps, because we know how to use our Q equation, right? We got a lot of practice with that last week's lab. So anytime we've got a temperature change, we know we're just using this Q equation. Anytime we've got a phase change in the flat spots where we have no temperature change. If there's no temperature change, we can't use this, right? It doesn't apply because delta T is 0. But we have something else happening. When we have a phase change, we're using these. They're in slightly different units this time. These are more standard units. We don't usually write our energy of phase changes as joules per gram, the way we did last week. More common in the chemistry and physics world to write it in joules per mole instead of joules per gram. But let's start with the temperature change parts first, because we know how to do those. So anytime you're not sure where to start with the stuff you know how to do. All of these sections, Q1, Q2, actually might as well keep them chronological. All of these sections that I labeled in purple, those all have delta T's. So for each of them, we're just gonna use that Q equation. What is different? Or what's? The emphasis there was weird. What's different between the Q? We're using the same equation for all of them, but what's changing?
The specific heat.
Well, I did give you 3 different specific heats all labeled, so there's a good hint that you're gonna need to use those. Sometimes I give you extra information, but if it seems like it makes sense, that's a pretty good hint. I don't always give, a red herring. Usually I'm gonna give you just the information you need, not a whole lot more. Always good to double check that. What else is changing? So we've got 3 different specific heats. Anything else changing? Is the mass changing? You had it the second time, Luciana. Yeah, the mass is gonna stay the same. Right, it's the same 135.0 grams of water the whole time. It's just, is it ice? Is it liquid? Is it gas? So for Q1. It's gonna be 135.0 grams. In this first step, it's still ice, so we're gonna use 2.11 joules per gram degree Celsius. And what's the delta T for Q1? We went from -23 to 0. Right, so when in doubt, look at where you started and ended. I know I didn't put any numbers to this one. We started at -23 and we ended at 0 for the Q1. And when in doubt, just plug it in, it's final minus initial. Our final is 0 degrees Celsius minus our initial, which was -23 degrees Celsius. So 0 minus -23 is +23. $135. As I'm not gonna rewrite this whole thing. What's gonna happen with the units here? Bingo. So we're just left in joules. Q should always be in joules or calories by the end. If we have a specific heat that's given to us in calories instead of in joules, we're just gonna end up in calories at the end, but it's still just an energy unit. Q is always an energy unit. Specific heat is always gonna be this weird combined unit. So 270 times 23. Get something in the 4,000 range, 5,000 range.
Times 10 to the 6.
Way off.
Maybe I won't. I don't think so.
Anybody else seeing that number?
That's.
You got 6,000? Okay, that's more, this is why it's good to do that reasonableness check and switch to a color that's easier to see too. Give me 3 sig figs.
6.55 times 10. I just got like 6,551.
There we go, so 6.55, you were doing it right.
Okay.
6.55 times 10 to the 3 joules. You find your error, Corbin?
Yeah, I did.
Yeah.
With the 23 for the temperature, didn't we have 2 sig figs?
Yes. I did only give it 2 sig figs there, so 6.6 times 10 to the 3rd then. Good catch. For Q3, mass stays the same. We got a different specific heat. And a different delta T, right? We're going from 0 to 100. So 135.0 grams, 4.184 joules per gram degree Celsius. Going from 0 to 100 means our temperature changes as 100.
But why do we have this?
We want to keep all the sig figs we're allowed to. But we have 4 sig figs here, 3 sig figs there. After we do the subtraction, that's only 2. No. Uh, 50 about. Something like 55,000. 56, 4, so 5.64.
Maybe 5.65.
5.65. Times 10 to the 4, correct? The 56,000, yeah. Right, so all of these ones with the temperature change. Some of the specifics change, but it's the same process every time. And the heating curve helps us organize our thoughts. It helps us see our delta T value. See what's changing temperature. So Q5 is still going to be 135. We're back to a different specific heat again, 2.03. Our delta T going from 100 Celsius to 125 Celsius. So that's going to be a delta T of 25. Which I didn't leave myself enough room for that. That should get something pretty close to this 6.6 times 10 to the third number, right?
Rounding, I have 6.9 to the 10 to the third.
So we're most of the way there. We did 3 out of the 5 steps now, right? What's left is the phase change. Phase changes. So for the phase changes, we don't have anything changing temperature. We're talking about these flat spots. What we do have energy is associated with the phase change. Okay, how are we feeling about this first part? Good if I clear the board? I don't see anybody actively writing, so I think we're good. So for those phase changes, we have melting and we have evaporation happening. And these are usually the way those are written, delta H of fusion. Don't worry about that H part. H is when you get into Gen Chem or if you keep going in engineering, you'll find out there's different types of energy, basically. Enthalpy is what we write as H. It's basically the energy in chemical bonds. So for this part, we're changing the energy in the chemical bonds because we're going from being solid to a liquid. We're going from being a liquid to a gas. So there's an energy associated with that. when we start, after we do this problem, we'll start talking about chemical reactions and we'll start seeing how changes in chemical bonds really can make a difference here. So. We have delta H diffusion, it's in units we're not used to. Kilojoules per mole instead of joules per gram. It's still just a combined unit though, right? When it was joules per gram. We would just say, okay, 135.0 grams. And for every 1 gram, it was 334 joules per milliliter. We use that energy as a conversion, right? Just like we would do with densities and just like we would do with speed. This is still just a conversion. We just need to get to moles instead of grams. How do we do that? This is another skill that's going to become really critical going forward, but we haven't done much practice with moles yet, right? We said what a mole was. We did a couple practice problems and we left it alone for a while. A mole, who remembers what a mole is? Not the number, you don't have to have the number memorized, but what is a mole? Remember we talked about if you had a mole of moles or a mole of ping pong balls. Basically just how many of something you have, right? It's just a counting number like dozen. So this is saying, instead of saying per gram of water, it's saying for every 6 times 10 to the 23rd molecules of water. This is how much energy it takes. So how can we go from grams of water to moles of water? Because once we get to moles of water, we can go to joules. That's our goal. We did a practice problem like this, and we did 2 or 3 of them, but it was a while ago.
Is it converted to kilograms, then kilograms to atomic mass unit?
You can go that route, but that's the long route. Right, so we can go from grams to kilograms, and then we have a conversion on our conversion sheet that says kilograms to AMU or atomic mass units, and then we can go from AMU into is per molecule. So remember those atomic masses on the periodic table. Let's look at oxygen. It's 15.999 AMU on the periodic table. So that's saying that 1 atom of oxygen weighs on average 15.999 AMU. AMU had a more useful form though. AMU is grams per mole. So we actually have a conversion just from the periodic table itself that tells us how to go from grams to moles. That atomic mass is grams per mole. So we don't need to go to kilograms of a single atom to AMU and then multiply by Avogadro's number. That's all taken into account with the definition of what an AMU is. We picked AMU very carefully back in the day so that we don't have to go the long route. So if we wanted to look at how many moles of oxygen are in 135 grams, we could just say, okay, well, if I have 135.0 grams of oxygen, every 15.999 grams of oxygen is 1 mole of oxygen. Right, those atomic masses are conversions. The problem is we don't just have oxygen, right? We have water, which is 2 hydrogen atoms for every 1 oxygen. So how do we get a similar conversion for water? Well, 1 water molecule has one oxygen, and two hydrogens, right? So we know the mass for the individual pieces. We just add them up. We can say, okay, if we wanna know the molecular mass of water. Well, two hydrogens plus one oxygen, so. Two times the mass of hydrogen, which, check your periodic table. Mass of hydrogen is 1.0078, so I'm just gonna go 1.008. And that's grams per mole. Plus we get one oxygen atom in there. So we took the atomic masses of the pieces and we just added them up based on the formula. As long as you know what the formula is for your compounds, finding the molecular mass is easy. As long as you have a periodic table. So take your pieces from the periodic table, we add them up. And we get a molecular mass of 18.015. I believe. This is now going to be our conversion that gets us from grams of water to moles of water. And once we're in moles of water, we can use these conversions to get to energy. So if we have 135.0 grams of water. Every 18.015 grams of water is 1 mole. And then we have our delta H fusion. So for our first phase change, going back to our heating curve, remember what we're trying to do here is get our energy for those phase changes, right? Our first phase change was melting. We're putting energy into a solid and it's turning into a liquid. So for every 1 mole of water that gets melted, it requires 6.01 kilojoules. So we had Q1, Q2, or Q3 and Q5 already done. This is Q2. The first plateau is gonna be what about 40 kilojoules? $135 divided by 18 is close to 0.75 times 6. Sorry, it's close to 7.5. 7.5 times 6. I guess probably closer to 50 kilojoules. 45, square in the middle. And we get to keep 3 sig figs here. So Ian, give me one more sig fig. Is there? Last piece. We need the energy for the second phase change. What changed for the second phase change? Did the mass of the water change? No. Did the molecular weight of water change? No. So just that last number changed. For boiling, we're just gonna take that 6.01. We're gonna replace it with 44.0. And that's gonna be a much larger number now, right? So Q 4 gonna be in the hundreds of kilojoules, maybe thousands of kilojoules.
I got 330 per rounding.
Which we want to make sure we know we're keeping that that's 3 sig figs. So you can use our shorthand, or you could put it in scientific notation. All right, so I know I erased a lot of the, I erased the temperature change part. But once again, this is gonna make the point that our phase changes take a lot of energy. Because if you remember, it was 6 kilojoules for this first step to go from -23 to 0. And then it was like 55 kilojoules to go all the way from 0 Celsius up to 100 Celsius. Then it was another 6 kilojoules or so to go that last bit. It's 330 kilojoules to boil the water. Way more than any other step that we did in here, like by a long shot. Phase change has a ton of energy in it, especially if it's a polar molecule. Because polar molecules have those partial positives and partial negatives, right? So they're stuck together pretty well. Those partial positives and partial negatives, you can think of them kind of like magnets. You think about how much energy it would take if you had, I don't know, let's say a bag of marbles. And you were gonna take all those marbles and you were gonna separate them out from each other. That's like vaporization. Marbles are not exactly stuck together, right? So it doesn't take much energy to take the individual marbles and separate them out. If I told you were gonna do the same thing with the same number of refrigerator magnets, it takes a lot more time to take a bag of refrigerator magnets and separate every single one out, right? It takes a lot more energy when we've got these polar molecules. All right, that was a long review problem. We've been in here for almost 45 minutes and we've done one problem. Well, 2 problems really. Draw the heating diagram and then get the energy. I like this as a test question. I'm not sure if this is on the test, if I'm gonna put it on the test exactly in this form, but I like it as a test question because it has a lot of steps. There's a lot of different things that I'm testing you on going through this process, right? Questions like this that have lots of different steps are really good questions for the final exam, at the very least for the take-home part of the final. When you have time to sit down and work through it, because none of this was inherently that tricky if you've been paying attention this whole time, but it's really hard to pay attention this whole time, and it's really hard to remember the right steps, right? So I'm not gonna pretend this was really simple. The individual steps, none of them seemed that bad, but putting it all together is the tricky part. That's what this class is about. All right, before we go to the next step, we actually have a good segue here. Why do we do things in moles at all?
Atomically accurate?
It's atomically accurate, but doesn't it seem like if you have a mass and we're looking up these numbers anyway, why go through the trouble of getting to moles? Because the number of atoms is actually how they react. They don't react grams to grams. Remember Dalton's atomic theory, the whole reason we got to atoms in the first place is because Dalton looked at the reaction of forming water from hydrogen gas and oxygen gas. He said it's really weird that it takes 2 grams of hydrogen for every 16 grams of oxygen. And then he said, well, if we combine them in a different ratio, if we keep 2 grams of hydrogen for every 32 grams of oxygen, we get hydrogen peroxide instead. So chemical reactions don't happen based on grams, they happen based on how many atoms we have. Because it's the atoms combining in these ratios that are actually going to dictate how things react. So things react on a mole to mole basis, even though we measure grams easier. Right, so what we're talking about today is chemical reaction. Whoa, I didn't realize that was animated. So chemical reactions is what happens anytime we've got a change in a system. And really, we can think of phase change as being a chemical reaction too. We can write it out as a phase change. We'll see that here in a second. But first I want to diagram out what the different parts of a chemical reaction are, so we're all using the same vocab. So a chemical reaction is anytime you've got a change in a system and we represent it with this arrow, called just a reaction arrow. Turns out chemists get very specific about the types of arrows. But for now, it's just a regular arrow from left to right. What that reaction arrow means is that we've got a before and an after. Before is what's on the left-hand side, and it's turning into what we have on the right-hand side. And the terms we use for what we're making, pretty straightforward. What the stuff we're making is called the products. Simple enough. The stuff we're starting from, we use one of 2 terms. The more common term these days is reactants. It's the stuff that's doing the reacting. The old school way, and we still see this sometimes, and there's a few places where I'll even still slip up and use this word, is reagent. Reagent and reactant mean literally the exact same thing. Frankly, I'm not sure why they changed it, other than reactant sounds more like reaction, I guess. All right, so all a chemical reaction is you put your reactants together, something happens, and you get your products. Anytime you've got a change that you can represent with a before and an after, you actually you can write it as a chemical reaction. So for our last slide, our practice where we were talking about liquid or solid water turning into liquid water. Well, that's a before and an after. But we can't really just write H2O turns into H2O. So if we're trying to represent water melting, solid water turning into liquid water, what are we going to use? These little symbols here in the parentheses, they're also written as subscripts usually. Sometimes you'll see them as full-size characters. These are just showing the phase of the reactants and the products. Right, so if we had solid water turning into liquid water, that's just ice melting. We just wrote it in a fancy way. And if we wanted to show boiling, it would be liquid water going to gas. Water is a gas. Does anybody know what this reaction is? What are the pieces that we have here? This is not, I would not expect you to be able to come up with this on the fly on your own, especially the first time you see this. I'm just asking. If anybody has any ideas? Something with a bunch of carbons and hydrogens reacting with oxygen, gas, making CO2 and water. It's fuel burning. Carbon, if you have a carbon or 4 carbons and 10 hydrogens, that's a molecule called butane. So this is butane burning. If you've ever used a cigarette lighter or like a lighter to light candles or something like that, you've done this reaction before. All right. And then there's one other phase that we came into contact with when we did nomenclature. Perfect. So because water is so common on Earth and it's usually a liquid when we come into contact with it under most circumstances. It's the most common, we call it solvent. It's the most common thing that we use to dissolve other stuff. And so a lot of times it's the most common way we have certain types of reactions happening is in an aqueous environment. Right, so aqueous just means dissolved in water. We've talked about that a little bit. So for those acids, we always write the acids as though they're aqueous, going back to our nomenclature practice. You see AQ, that's all that means. If you had a solution where the solvent wasn't water, you would actually just have to provide more information. We don't have a shorthand for everything. So like in organic chemistry, a lot of times we'll use benzene as a solvent. We try not to because it's a carcinogen, but sometimes it's the best solvent we have. So you'll see things like, I don't know. And then underneath it, it'll just say in benzene. We don't have a shorthand for the phase for in benzene because it's such an uncommon situation in most circumstances. We've got an issue with this reaction though. On the left-hand side, we have 4 carbons. But on the product side, we only have 1 carbon. But we can't just destroy matter. All the carbons that we started with have to go somewhere. And actually, we've got a lot of mismatches, right? Because we have 2 oxygens on the left-hand side and 3 on the right-hand side. We can't make oxygen out of nothing. So what do we have to do? What's going on here? If we think about this, I'm gonna switch this away from being an abstract idea like a chemical reaction, and I'm gonna write a recipe like a chemical reaction. I like to use cheeseburgers as an example. What goes on a cheeseburger? Simplest cheeseburger you can have. Meat, cheese, bun. So we've got, I'm gonna call the bun bread, because we can talk about 2 pieces of bread. You can't have half a bun. You can't have just the bottom bun and still call it a hamburger, right? So we've got a patty plus cheese plus bread makes a hamburger. We all agree that that's a cheeseburger? Is that all the information we need, though, to make a cheeseburger? What else do we have to specify? 2 pieces of bread is a good example. We can't just say I need bread. I need 2 pieces of bread per hamburger for this to work, right? And I don't know, if you're like me, 1 piece of cheese doesn't usually seem to be enough. So in the interest of just making the numbers more interesting, I'm gonna say we're gonna put 3 pieces of cheese. It's more like a grilled cheese with a hamburger patty on it than it is hamburger at that point, but that's semantics. So to make our version of a cheeseburger, we need a patty, we need cheese, we need bread, but more specifically, we need 1 patty, 3 pieces of cheese, 2 pieces of bread, makes 1 hamburger. And so these numbers that we put in front we call those coefficients. And all they are is just how many things we need in order to combine them in the right ratio. If you tried to make a cheeseburger with 17 pieces of cheese, then we really have a problem, right? That's, I don't know, that's like half a pound of cheese. We can't put that much cheese on a cheeseburger, it's just not reasonable. Right, so if you mess with these ratios, it messes with what your product is. And so that's what Dalton was figuring out when he figured out that, 2 grams of hydrogen for 16 grams of oxygen makes water, but 2 grams of hydrogen for 32 grams of oxygen makes hydrogen peroxide. Changing the ratios changes the recipe. And what's really changing is these coefficients. So all that's missing here is we need the right coefficients in the right places so that we have the same number of pieces before and after. You have to end with the same number of atoms that you started with and the same types of atoms. Unless we're doing a nuclear reaction, if it starts as a carbon, it has to end as a carbon. And we call this process balancing the reaction. Reaction has to be balanced. If this was the 1990s, I'd say you balance it like you balance a checkbook. Money in and money out has to add up, right? Nobody actually balances checkbooks anymore. So that analogy doesn't work as well, but we still need to end with the same number of atoms we started with. So if we start with 1 butane molecule, 1 CH4, how many CO2s can I make? So I'm going to use another macroscopic analogy. There's four carbons in this butane. So let's pretend we're talking about a 4-door car. If a car has 4 doors, if you take all the doors off, how many doors do you have? 4, right? It seems like when I put it that way, it's such a simple question that it almost seems like a trick question. If I have 4 carbons and I take them all apart to make CO2, how many CO2s do I get? Right, because every carbon I pull off this first molecule can turn into a CO2. And now I have the same number of carbons before and after, right? I started with 4 carbons on this side. If I make 4 CO2s, I've got 4 carbons on the right-hand side. What about the hydrogens? I've got 10 hydrogens on the left. And all of the hydrogens that I have go into making water. And every water takes 2 hydrogens. How many waters can I make from 1 butane molecule? Exactly. We've got a total of 10 hydrogens on the left-hand side. And I'm going to turn all of those into water so I can make 5 water molecules. I can't just take this and turn it into, I can't just say, oh, I'm going to make H10O. That's not water anymore, right? We can't change the subscripts because that changes what our chemical is. Once we get our reaction written, we can change how many of a molecule we have, but we can't change what that molecule is. So now our carbons are balanced because we had 4 carbons on the left and we've got 4 carbons on the right. Our hydrogens are balanced because we got 10 hydrogens on the left, 10 hydrogens on the right. What's left to balance?
Oxygen.
Oxygen. How many total oxygens do we have on the right hand side? Yeah, we've got 4 CO2s, each CO2 has 2 oxygens, so that's a total of 8. Trying to make it so it doesn't just look like an 80, but I made that worse. 8 oxygens. And then we have 5 oxygens here, right? For a total of 13 oxygens. How many O2 molecules does it take to get 13 oxygens?
6.5, but you can't have 0.5 and 2.
We can say 6.5. If it's a total of 13 atoms, we can't have half of an atom or half of a molecule. So we're only gonna balance these in whole numbers. Go back to our car doors analogy. If I'm taking car doors off of something, there's no way I can get half a door. I mean, that falls apart if you look at it too much, but you see what I'm saying.
But we have to double all the quantities so that we can do 12.
So the way I usually say that, what's the easiest way to make an odd number even? Is to double it. If we can't have a total of 13 oxygens here, because there's no way we can get to 13 oxygens with a whole number here, we just double the first number. Which is then gonna double our carbons over here. Which is gonna double this. Because now I've got a total of 20 waters, so I can make 10 H2Os. Now I've got a total of 26 oxygens. And that's an even number, which we can get O2. Takes 13 of them. So this is why we do things in moles. Is because the reactions happen in moles. We balance the reaction in terms of moles. Because it's all about how many atoms we have in order to make things happen. If you're trying to get, like, why do we care about this? This tells us something about how many molecules of everything we need. It's kind of surprising, you need 13 oxygen molecules for every 2 butanes for it to burn properly. Burning butane requires kind of a lot of oxygen. It's not just as simple as put equal amounts together. If you put equal amounts of oxygen and butane together and you try to burn it, you're gonna run out of oxygen. Going back to our hamburger analogy. If I had equal amounts of hamburger patty, cheese, and bread, I'm gonna run out of cheese before I run out of everything else, right? Because I'm not using them at the same ratio. And so anytime we have a mismatch like this, it means our reaction is not balanced. In our first step, once we get a chemical reaction, sometimes your first step is actually writing this out. And as you get further and further into your education, you'll wind up with different ways of describing this. If I was describing this to one of my OChem students who's had 2 years of chemistry now, I could just say butane burns an oxygen. Write it and balance it. They should be able to write this and balance it pretty easily because they've done this so many times. They know that a combustion reaction means put it in oxygen and you make CO2 and water. You all don't know that yet, and that's fine. So for this class, I'll do things like butane, C4H10, reacts with oxygen to make CO2 and water. I'll give you all the pieces, maybe verbally or written, and then your job is to then use your nomenclature skills we just learned to write it out like this and then balance it. Right? Or I'll give it to you like this on the test. The way that I'm gonna give you these reactions is I'll say, here's your reaction, here's blank spaces. Balance it and then do some math with it. And so this is going to be one of those skills that winds up being really important. If you can balance these reactions, that's at least 12 points on the final. 12 out of 100 is going to balancing these reactions. All right, let's take our break. When we come back, we're gonna practice balancing reactions. Here's a bunch of reactions, let's balance. Let's come back at 11:30.
Thank you.
If you don't have your polyatomic ion quiz back yet, grab it.
Yeah.
Oh, that's right, I forgot that. Yeah.
That's a slightly different.
It's 1 to 4, it's 35.
Oh, and.
Melody? Brandon.
I don't want to get.
Yes, that's a good one to bring us back.
Big bang, she's like.
Oh, Okay, so just one lecture afterwards, read the slides, and then, can you come to, your labs today, so it's just lecture? Thanks for letting me know. You good? And also on that that's was actually a question I was trying to answer this weekend. Who else is on that interview panel?
I'm not. I know there's gonna be representation from the boys team and then as far as faculty.
Okay, cool, thank you.
Sorry.
No worries.
Take like an extra math. She said so.
Okay, sure. I thought it was really convenient. I thought it was really good. I'm writing it and I look at it, it's like, I'm thinking about, but it's still on there. So it's interesting. Still got to be- There's my chemistry. These two. We need to have like one of those to like, I would take this one out. This is what I'm saying or something. This other person. I took these three, I already passed these. It's just a bit of extra classes or break through. Besides nice. For like. She's taking all like. So my daily lift. Yeah, so I'm feeling. Okay. It's just like. That's a sick. But the whole time, it's not that. But they're trying to push me. Yeah. But I can help the other school. Supposed to come. What you trying to? Then start. I'm like trying to. And then I'm like, you know, it's kind of. I'm like, no, it didn't. Trish. I don't think it's ever so long before 6. It's usually there. And it's like the aromas. Somebody, I don't. It's like, you're done, so, yeah, until you hit the doors, because. Turns out, once you hit like the upper area, it'll be fine. Be okay. No. No, that'll avoid it. I'm like, okay. I can't stand still. Neither, I can't do it. I'm so self-conscious about me too. You're good. I don't know if it's me. It's like this. It was already here. Not good. I'm not going. You're not? No. Steve's like. I got class that day. Like, what? Steve wants me to sit on like the interview panel since I'm leaving for the coaches next year. See, they still don't know. They're just now starting in movies. Yeah. Oh, and it's just the first round. So it's with me and then I'm starting to pick with Josh. Because he's obsessed with Josh. So he's like, you know, like I would love to, but I have too many classes. Like, you could find somebody else if you can't. Like, no, but like, I know we can't. Can you? Fine. This whole. No, it's downstairs somewhere. I guess they're doing the first round on Zoom and the second round in person. I could just make it all. Yeah, if you want to, you know, it was really committed and you just have everything where, it's so good. But yeah, they're just not starting. Yeah, they're just not starting. That's insane. The committee. It's good. It took that into finding the courses out in this position. Well, they had to redo the job listing in so long. So it's okay. I should take you about the day to do it. Right. Close that shit down. Maps. There's no way to get it go. Or just slow them, and that's who's in charge of it. That's the majors. Is that Gatorade? Yeah. Yeah, I'm gonna use it. This. You don't feel like you need it. Exactly. Sure. Did you say source? No, because we go down. Yeah. So that's what we're on. My old thought has a doctor's appointment and I'm sure the biggest is. Well, yeah, I'll be on the classes for them. Yes, they can't. No, okay, my goal is with the English models. I used to have one But the name was Lady Grace. Oh, boy, I'm very sorry. Yeah. 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 No. But yeah, but like us. That's first. So, I think it's very good. You just all this is weird. Everything is out there. I don't think it is either. Yeah.
Alright, as everybody's coming back in here, let's go ahead and start working on some of these. And Jalen, you're gonna come by lab a little bit early, take the other one. Oh.
There. Oh my God, so I think I can even try. So it's good. So it's like, okay, it's more. I was so nasty. That's all. But he was like.
Also, if you're struggling with the first one's the trickiest one out of all these. So you might try B, C, and D and then come back to A.
Yeah. Right.
No, so anything in the phases is not part of balancing. Basically, it's just saying the reaction's happening in water. In water, it's part of the reaction, but then at the end, you just get this HCl that's dissolved in water, it's still there.
So just give us, I realize that's not. And he didn't even speak about we were on there. That's daughters, you should know this, so next year you guys will get the patients, it's gonna buy, it's gonna make sure. Sorry. No. It'll pay for it. That was the thing, our budgets. Up by there. And then where's that money that we raised? So you're where is it?
So these are a little bit like those logic puzzles from fifth grade, where so and so is taller than Jimmy, but shorter than Jan. It takes a little bit of practice, but if you can work out some. Like, so for example, for B. I've got a nitrate here, that's my only source of nitrogen, is nitrate from over on this side, right? But I have two nitrates and then another nitrogen showing up over here. So I've got at least 3 nitrogens on this side. So at the very least, I know there has to be at least a 3 there. It might be more than 3, but it's gonna be at least a 3. Right, because that's the only possible way we can get 3 nitrogens on this side. If you do that, now my nitrogens are balanced. And actually that took care of the oxygens too. Maybe. I gotta get rid of this slide because it says 2 tricky ones at the top and then the bottom ones are easy.
I mean, if you did like three, you get 3 nitrogen.
So, but then we haven't even, so we're gonna use another logic step here. There's an even number of hydrogens on the right-hand side. Which means we have to have an even number of hydrogens on the left-hand side. There's no way we can ever make the hydrogens on the product side equal an odd number, right? So it can't just be a 3 here. It has to be at least a 3, but it also has to be an even number. Right? Because if the nitric acid here doesn't have an even number in front of it, then we're not gonna get an even number of hydrogens on the right-hand side. So it can't be a 3, it has to be at least a 3 because we have 3 nitrogens showing up on the right-hand side. But it also has to be an even number, so basically this is glorified guess and check. I know it's gotta be at least 3 and I know it has to be an even number, so I'm gonna go with the lowest even number that's greater than 3. And I'm gonna change that 3 to a 4. And see what that does. Our nitrogens and oxygens here are still good. Now we've got 1 extra nitrogen, so we could maybe put a 2 there. Now our nitrogens are balanced. We had 4 hydrogens on the left now. Only 2 here. What if we did that? Did that fix everything? Copper's good, we had 1 copper before and after, we don't need to mess with the copper yet. Our nitrogens, 4 nitrogens on the left hand side. 2 there, 2 there, 4 nitrogens on the right hand side. Got 4 times 3, we got total of 12 oxygens. 6 oxygens here. Plus 4 there, that's 10. Plus another 2 oxygens from the water. So that's a total of 12 oxygens, so our oxygens are good. And our hydrogens, we have 4 hydrogens here, and now we have 4 hydrogens on that side. And our coppers are good, 1 copper and 1 copper. So it looks balanced to me now. And again, this is about as tricky as it gets. The trickiest thing about this one is that you got nitrogen showing up in 2 places and oxygen showing up in in 3 places. On the right hand side, that's when it's always going to get the trickiest. It's when you have same element showing up in multiple places on one side.
I have a question about A.
Okay,
I guess it's a question about the answer, but I'm unsure. To balance it, I just made it 2 HCl on that side, and I believe that balances it. Am I correct?
so your oxygens were already good. Because we had 1 oxygen on the left and 1 oxygen on the right. Chlorines are gonna be tricky because they show up in 2 places, right? And I just told you that's one of the trickiest things to do. So sometimes with that, when you've got some of the same thing showing up in 2 places, start balancing everything else and see if it resolves itself. Which in this case, if we just balance the hydrogens. Because we have 2 hydrogens here, we know we have to have an even number of hydrogens here, we have to have an even number of HCl's. Right, same logic I used on B. So if I look at 2 there, hydrogens are good, oxygens are good, and that took care of the chlorines too. Right, and phosphorus we never even had to touch, just like copper. So a lot of times, if you can figure out Just like those logic puzzles, if you can figure out that I know this connection, I know that these two have to be relative to each other. That'll give you a bit of a foothold, so it's not just guess and check. It still is gonna feel like guess and check as well, we figure out how to do this, while we get used to it. But the nice thing about this is it's really easy to check your answers, even if it is guess and check, we're only dealing with whole numbers. And you can always just plug stuff in and then see what happens. Let's do an easy one. Let's do C. Hydrogen gas plus iodine reacts to make hydrogen iodide as a solid. If it was dissolved in water, it'd be hydroiodic acid. Even number of hydrogens on the left-hand side, odd number of hydrogens on this side. So what's the easiest way to make an odd number even? You double it. That took care of my hydrogens. It also took care of the iodines. Generally speaking, whatever the last element you're going to balance is, will usually take care of itself. Because if everything else is balanced, then your last element is going to be balanced as well. What about D? So iron rusting. Iron plus oxygen turns into iron 3 oxide. What do you see about them? What's the total? What's the first place that you can see? I know this about this reaction. Give you a hint. Has to do with odd and even numbers.
There's gonna have to be an even number of Fe2O3s.
Right, we have an odd number of oxygens on the right hand side. But we can only add oxygen in even integers. So we have to make our oxygens even. Easiest way to make an odd number even is to double it. Now we've got 6 oxygens on the right hand side, which we can balance. That takes care of our oxygens. And since iron is all by itself, that's the easiest thing to balance last, because we can put whatever integer we need in front of the iron. In this case, we've got a total of 4 irons on that side. Right, 4 irons, 6 oxygens, 6 oxygens, we're good. I guess maybe a better analogy than those logic puzzles is it's like doing a Sudoku puzzle. You've ever done those before? You're trying to, okay, I know that this block has to have a 6 in it because I'm missing a 6 in this row. Things like that, using similar logic to balance these. And the mathematicians will tell you, it's all the same math. It's just linear algebra. Where you can set up matrices, when the math instructors are teaching linear algebra, which I think is what's going on, I think that's this quarter right now. They ask me for difficult chemistry reactions to balance, because you can balance this using a matrix and using some matrix algebra. And then it's not guess and check. Generally speaking, it's more trouble than it's worth, since everything's integers anyway. It's not too hard to do it by hand. There are a couple that you can come up with that wind up with like a 17. That it might be easier to balance with the matrix, but. All right, let's do another practice. This isn't butane burning in oxygen, this is propane burning in oxygen. Similar reaction, except the balancing is going to be different. We don't know if this first one's gonna be a 1 or a 2, but let's assume it's a 1 for starters. From there, we can get our carbons and our oxygens done, right? 1 propane. You've gotta be able to make 3 CO2s. Carbons are good now, right? What about hydrogens? How many waters can I make? Got, yeah, I've got 8 hydrogens. Each water molecule takes 2, so I can make 4 of them. 4 times 2 is 8. Then last thing to do is look at oxygens. We leave oxygen till the end. Because I can add more oxygens without changing anything else, right? So it's the easiest thing to do at the end. If I go back and I change this, or if I have to change CO2 later, that's gonna change, that causes a chain reaction where I have to change everything. So we always leave whatever you have by itself to the end. In this case, that total is 6 oxygens plus another 4, so that's 10 oxygens. 75 O2s. Alright, so these things take practice, like everything we do in this class. But at least it's easy to check your answer and know if you got the right answer. So, silver linings. Let's go back and review that other skill we reminded ourselves about. How many moles are in 5 pounds of propane? If you have a 5-pound tank of propane, how many moles of propane are in it? So propane is C3H8. Have a mass, force technically, but we'll call it a mass. This is just a conversion problem, right? We can go pounds, grams. Then we can use the molecular mass like we did at the beginning of class to go grams, moles. First step's easy, right? That's on our conversion sheet. You know how to go from pounds to grams. Grams to moles depends on what the formula is, but you've got your periodic table. So 3 carbons, carbon is 12.011 AMU, right? 4 grams per mole. And we've got 8 hydrogens. So 36 and 8 is gonna be 48, 44 or so. .0 44.11 maybe.
0.097, so 44.1.
We'll go 0.97. We get to keep all the sig figs off the periodic table. Because we're doing addition, we get to keep our uncertainty to the same decimal point, right? So We get to keep it all the way to the thousandth place. Now that we have that number, I'm gonna erase this part. Just because we don't wanna leave it to just one single thing, let's assume that when we buy our 5 pounds of propane, they actually filled it up to plus or minus a tenth of a pound, so we get to keep 2 sig figs. Every 1 pound is 453.59 grams. Just from our conversion sheet. That'll always be true as long as we're on Earth. Then we can say for every 44.097 grams, that's 1 mole of C3H8. Get something close to 50. Say it again.
51.
51. Alright, so here's to drive home the point that the reaction happens in terms of moles. Now that we're in moles, this is how many molecules of propane we have, right? This is just a way to count molecules. And we balance the reaction in terms of molecules. Every 1 propane uses 5 oxygen molecules. Or every 1 propane that burns makes 3 CO2 molecules. So how many moles of CO2 will we make if we burn all 5 pounds of propane? That's 51 moles of propane reacting. How many moles of CO2 does that make? It's not 1 to 4 now, so let's use a tricycle. If I started with a tricycle, I started with 51 tricycles. And I took all the wheels off. How many wheels do I have? How many, Brooke? Oh, sorry, if I took all 51 tricycles, I took all the wheels off and I put them in a pile. I have 51 times 3. 153. How did we know to do that? Because we basically wrote a conversion factor and said 1 tricycle is 3 wheels. Replace tricycle with C3H8 and replace wheels with CO2. For every 1 propane, that's 3 CO2s that get made. These coefficients, once it's balanced, these coefficients are conversion factors too. Because it lets us say for every 1 mole of propane that burns, I can make 3 moles of CO2. So instead of 100, saying it's 153 wheels in my pile of tricycle wheels over here, I can make 153 moles of CO2. Right? If we balance it properly, all of these coefficients are conversion factors relative to each other. You can also do things like, every time I make 3 CO2s, I also make 4 waters. Or every time I take apart 1 propane, I use 5 water molecules, or sorry, 5 oxygen molecules. Right, that idea of using the coefficients as a conversion factor has a big scary chemical name called stoichiometry. Stoichiometry, I would guess it's Greek originally because of this OI in there, but I don't really know. Seems Greek. It's all Greek to me. All stoichiometry is using this conversion factor. It's starting from a balanced reaction and then converting from moles of one thing to moles of another. Alright, so this is the other part. Remember I said that there's gonna be 12 points that are balancing reactions? The other points on those 3 problems on the final are doing this. Once you balance it, then you tell me how much product you can make, or you can tell me how much of reactant is left over. That's all it is. It's basically just logistics issues. What do I run out of first? How much can I make? And it all comes back to this idea. All right, we already did the cheeseburger analogy. So I'm gonna rewrite our cheeseburger equation. We said 1 patty plus 3 pieces of cheese plus 2 pieces of bread makes 1 hamburger. Let's say I go to the store and I buy a loaf of bread that comes in 16 pieces of bread. And I buy a pack of pre-frozen patties. 10 patties. How many hamburgers can I make out of 16 pieces of bread and 10 patties? I have enough bread to make 8 hamburgers. I guess technically if it's a loaf of bread, then technically patty melts, but let's not split hairs. If I have enough patties to make 10 hamburgers and enough bread to make 8 hamburgers, how many hamburgers can I make? 8. Right? I don't get to just add these together. That would be silly, right? To say I have enough bread to make 8 hamburgers and enough patties to make 10 hamburgers, therefore I can make 18 hamburgers. That doesn't make any sense, right? For whatever reason, when I replace bread and patties with chemicals, all of your logic will go out the window. You're gonna forget about that logic. The whole reason of using this analogy is to show you that it's the same thing that applies to chemicals, to molecules. So let's do it with molecules. So conservation of mass that we've talked about before means that we have the same number of atoms before and after. It doesn't mean we have the same number of molecules before and after. This is another thing that can trip people up sometimes. We go back here. I took 16 pieces of bread and 10 patties and turned it into 8 hamburgers. I have fewer molecules at the end than I started with. I have fewer pieces because I put everything together, combined everything, right? That doesn't mean I lost anything along the way. It just means I rearranged it so that now instead of having separate bread and patties, it's all put together as one object that we're calling a hamburger. So let's do this reaction with aluminum and bromine. If you let aluminum be exposed to bromine, you make aluminum bromide. Start by balancing the reaction. Look at your odd and evens, right? Do the phases matter for balancing? Do we care if it's solid aluminum bromide or liquid aluminum bromide? Not really. That'll matter when we actually get to like the practical aspect of we're going into lab and we're actually gonna do this reaction. We actually care about the phases then, but for now, if we're just trying to balance the reaction, it doesn't really matter. We can leave them off. So I've got 6 bromines on the right, I need 6 bromines over here. 2 aluminums. That look good? So if I want to react 3 moles of bromine. How much aluminum do I need? Seems like 2 moles would make sense, right? If we want to show that mathematically, if you're not seeing it, this is what I mean by when we switch out hamburgers for chemicals, it makes it seem a lot harder than it is, but it's still the same math, it's still the same logic. If I want 3 moles of bromine are going to react. Well, for every 3 moles of bromine, it takes 2 moles of aluminum. I just pulled those numbers straight from the balanced reaction. Right, for every 3, and you can just, if it helps you keep track of what's going on, just add some descriptive words, reacted. 3 moles of bromine reacted, so 2 moles of aluminum reacted. In this case, 3's cancel 3, we just get 2 moles of aluminum needed. What if we make the numbers not so neat? We have 1 mole of aluminum. We're still just gonna set it up like a conversion factor. Maybe, and I don't think I stressed this very much. I put bromine on the bottom here because I want bromine to cancel out. We have moles of bromine on top, so I put moles of bromine on bottom, so it's gonna cancel out, just like a conversion problem. It is a conversion problem. If I want moles of aluminum to cancel out, I'm gonna start by saying, okay, 2 moles of aluminum goes on bottom. And whatever I'm trying to convert it to goes on top. I want moles of bromine, so I find my moles of bromine, it's got a 3 in front of it, 3 moles. Every 2 moles of aluminum that reacts uses 3 moles of bromine. Right, so same logic as our hamburgers, or same logic as our wheels from a tricycle. It's just with chemicals now instead. This is how we show the math. Just remember how when we first did conversions, we started with conversions you knew how to do in your head already, right? Like feet to inches. Everybody already knows to go feet to inches, you multiply by 12. We started showing our work for that by writing conversion factors. So that when it got trickier, we could do it. Same with wheels and trikes. We could figure out, oh, I'm just gonna multiply by 3. That's easy enough to do in your head. But when it's chemicals, that makes it more abstract. That makes it harder to wrap your head around. And especially if it's not whole numbers. We know that the balancing is always gonna be whole numbers, but this isn't always gonna be whole numbers. So we show the work like this for the easy ones, and that's gonna help us down the road. Let's do the last problem here. We're trying to make 8.51 moles of aluminum bromide. How many moles of bromine did I start with? Well, for every. If we're trying to make aluminum bromide. We come back to the balance reaction. For every 2 moles of aluminum bromide. Made. That's 3 moles. Of bromine gas or bromine, yeah, it is a gas here. Used. We can fill in used or reacted because we know it's on the left-hand side of the arrow. So we know it's being used up, it's reacted. Might have been 12.76, I think.
Yeah, 7.7 after round.
And actually, we're only gonna round it. We're gonna round it to 3 sig figs anyway, so. So, to go back to the question I asked at the beginning of class, why do we bother doing things in moles anyway? Why not just leave it all in grams? Because this conversion factor gets way messier if we try and do it all in grams. And balancing the reaction gets almost impossible to do it if you're trying to do it in grams. But as soon as you put it in atoms and moles, it's really straightforward. It's all whole numbers, it's all integers. Our conversion factor looks pretty easy to wrap your head around. And so a big chunk of the rest of this class is going to be, here's the reaction, here's your starting material. How do I get it to moles? And how do I figure out how much product I can make? Right, it's doing this over and over again. All I can change basically is, how do we get to moles? The first thing you're gonna do is balance it. The second thing is whatever I give you, put it in moles. Right now, we only have one way to get to moles, and that's using the atomic mass. All right, we're going back to hamburgers for a second. If I buy, let's write our balanced reaction. Patty plus 3 cheese plus 2 bread makes 1 hamburger. And I don't think I actually said this, that's kind of implied. If you don't put a coefficient in front of something, it's assumed to be 1. Just the same way we don't write over 1 every time we have a number we write down, we don't always have to put 1 in front of it. But for the sake of us learning this the first time, let's put a 1 there. 1 patty plus 3 cheese plus 2 bread equals 1 hamburger. If I buy half a pound of cheese and 1 pound of hamburger meat, how many hamburgers can I make? Yeah, we need the atomic mass of cheese, we need something, we need some more information, so in this case, we can estimate it, we can use our. Our intuition, but if we wanna show our work, I don't know how many slices of cheese are in half a pound of cheese, or in a quarter pound of cheese. I'm gonna say like those pre-sliced things you get are usually like half a pound of cheese, and they come with like 16 pieces of cheese probably. Does that seem like a reasonable number? Who's been to the grocery store recently? So let's say that instead of using an atomic mass of cheese, our conversion will be every 16 slices of cheese is 0.5 pounds. Seems reasonable, I guess. What about hamburger? How many patties do we get out of a pound of hamburger meat? We'll go with standard McDonald's style. Quarter pound of meat per patty. So 1 pound is 4 patties. So how many hamburgers can I make? Well, I have 0.25 pounds of cheese. In every 0.5 pounds is 16 slices. And for every 3 slices of cheese, 1 hamburger.
Would it be 0 burgers?
Good question. If it's not specified, usually we assume we're not gonna run out of it. We assume this bread's cheap. So let's give more context here. You and your 2 roommates are buying supplies for cheeseburgers. And you're all responsible for bringing 1 ingredient. Whoever's in charge of bringing bread, they got the easy job, they're just gonna buy a loaf of bread, there's plenty of bread, right? So we assume we're not gonna run out of bread. We have enough cheese to make. So 8/3. That gives us what? 2.67. Where's Bianca? Versus, I have enough hamburger meat to make 4, right? I can see that already, but let's show that. 1.0 pound for every 1 pound of patties, that's going to be 4 patties. And for every 1 patty, I can make 1 hamburger. So I have enough hamburger meat to make 4 burgers. But the cheese, I only have enough to make 2.5. 2 2/3 hamburgers. So what's gonna run out first? Cheese. In this case, the cheese is what we call the limiting reactant. Limiting reactant is just a fancy way of saying what you run out of first. Because what you run out of limits how much product you can make. You can't keep making hamburgers after you run out of cheese, at least if you're following our recipe. So this step here, this is the analogy we're using here is, we would be using the atomic mass to get from grams to moles, instead of going from pounds to patties. But it's the same idea, it's called starting from the mass, we can still do stoichiometry, we just have to put it in moles first. Let's go back to this reaction. If you have 25 grams of aluminum, and assuming you're not gonna run out of bromine. So to indicate that, a lot of times we'll just write excess. Excess just means you're not running out of it. 25 grams of aluminum with excess bromine. How much product can I make? First thing we have to do is put grams of aluminum into moles of aluminum.
And this is the first.
So for that, we just need the periodic table. Right, aluminum's got a mass of 26.98. So we can find our conversion factor for every 26.98 grams of aluminum. 1 mole of aluminum. We're halfway there. We're trying to get to moles of aluminum bromide. So now we just look at our balanced reaction. For every 2 moles of aluminum, I can make 2 moles of aluminum bromide. So sometimes with these stoichiometry conversions, you wind up with a step where nothing actually changes. Right? Because 2 over 2 is the same as multiplying by 1. So it's not really going to change anything. Right? We still want to show that step though, because this is the step that allows us to cancel out moles of aluminum and be left in moles of product. If you get really comfortable with stoichiometry and doing these problems, for this class, you have to show this step even if it doesn't change anything on your calculator. You get to Gen Chem and you get really comfortable and you show me that you're really comfortable with stoichiometry, then we might relax that and not have to write that step out. But for now, I want you to show that step. So it's gonna be something a little under 1 mole, right? We get 0.9 what? 2, thank you.
You round 3.
3, perfect. How many grams is that? And then we'll be done. We made 0.93 moles of aluminum bromide. How many grams of aluminum bromide did we make? Well, we can use the molecular weight or the atomic mass to go from grams of aluminum to moles of aluminum. We want to go from moles back to grams. We're just going to use the molecular mass again. We just have to do the molecular mass of this whole thing, not just the aluminum this time. So 1 aluminum plus 3 bromines is a much larger number, right? Bromine's got a mass around 80.
We did the division across 26.58, that wound up with 0.93. Then we have to divide again
Wow.
in order to get the aluminum bromide.
So it's just because the bromine is there doesn't mean it's part of this conversion factor. Because we know we have enough bromine, we're not running out of bromine, so this conversion factor is just gonna be multiple amounts, multiple amounts of bromide.
Just one, I get it, okay, thank you.
So 26.98 plus 3 times 79, no, 79.9 or something like that. I don't have bromine memorized. 79.50. So something like 260. $58.5. That look right?
265.48.
265.48, thank you. If I wanna know how many grams product I make, we're just gonna use that. Now we want moles to cancel out, so we're gonna put one mole on bottom. And 265.48 grams on top. We get a number that's much larger than 25, right? Something around 250. Just under 250, 240 something. Where did that extra mass come from? How come we used 25 grams of aluminum and we ended with 250 grams of product? It's not the same molecule anymore. It has the same number of aluminum atoms as what we started with, but we added it, we combined it with bromine. So the difference in mass is gonna be how much bromine was used. All right. That whole process is called a mass to mass stoichiometry conversion, or stoichiometry problem. You started with the mass of reactant, you figured out the mass of the product. And that's gonna be something we're gonna spend a lot of time with. Our whole first half of class on Wednesday is gonna be practiced with this. Right, so balance reactions, get everything in moles, use your conversions. All right, I'll see half of you in lab. Should probably most of everybody who's here, and everybody else will see you on Wednesday.